Go ahead.
Thank you very much. Yeah. So last session on convergence and continuity of star products, and up to now we've seen the flat case with a constant Poisson structure. We have seen some applications in quantum field theory to make things a little bit more non-trivial, but also in finite dimensions. This is an interesting scenario, and I've shown you last time the linear case of a linear Poisson structure, which is the same thing as a dual of a Lie algebra, and to implement continuity there. And as it was also in the discussion, you can view this as the task of finding a topology on the universal enveloping algebra such that it becomes a locally convex algebra with a hopefully large completion. And this was the model for it if you want a simple calculus for the universal enveloping algebra. And today I really want to do a bit more geometry, and this is a newer result. So this is the example. I should go back to the thick thing here. The example of a cotangent bundle of a Lie group. And that's a very recent preprint with Oliver Roth and Michael Heinz. I decided to give you references for all these things and credits to all the people involved at the end, and I will write down the precise references in this lecture notes here, and so you can look them up here. So okay, so for that I have to recall first a little bit how to cook up a star product on a cotangent bundle. Yeah, I mean, of course we have these general existence theorems and constructions of many people, and but we, in order to do estimates, you have to get pretty precise formulas. Yeah? So I would like to recall a construction done in the 90s by the former Freiburg group with Martin and Nikolai Neumeier here and myself. So so first the general construction of a simple calculus, and which is the same as a star product. Star product on T star Q any configuration space. So that will be a smooth manifold, not necessarily a Lie group. Later on, it will be a Lie group. Yeah? So what do you do? Well, the first observation is that what we did with vector spaces also works with vector bundles. So we have the polynomial functions on the cotangent bundle. That will be those smooth functions which, restricted to a fiber, will be polynomials. That is graded by polynomial degree. That can be viewed as sections of the symmetric tensor powers of the tangent bundle, and direct sum of those sections. And there's this canonical function linear isomorphism. This is the canonical C infinity Q linear isomorphism, algebra isomorphism, I should say algebra. Isomorphism, also respecting the grading. And well, how do you do that? Well, a polynomial of degree 0 is just it's a function on Q that is pulled back to the cotangent bundle, and a linear a vector field in here that is turned into a linear function on the cotangent bundle. So I only have to specify it for these degrees. So let's take a guy in here. Then that is mapped to J of U, which is just a pullback with a bundle projection. So T star Q is always viewed as cotangent bundle, and I will also use the zero section with the iota. Yeah, so that's J on degree 0, and on degree 1, it is that's the map which that is defined by, well, J of x at a point alpha q is alpha q of x of q. Yeah, so alpha q is an element in the fiber over q. Yeah, so alpha q is some element in the in the fiber over q. Yeah, and q is a base point. So that's and then you extend it but to be an algebra homomorphism, and it turns out to be an algebra isomorphism. So that's the thing we used yesterday a lot, and now we are sort of in finite dimensions, even though it's no longer over a field, it's over this ring of functions, but there it's really an isomorphism. Okay, and maybe I said that I always wanted to do complexified, complex valued functions, so I should complexify the bundle here as well to make it really an isomorphism. Then the next ingredient we need to cook up a simple calculus is a covariant torsion-free connection nabla on Q. And so we extend this as usual to act on all kind of bundles, and in particular this will give us a symmetrized covariant derivative, which I denote by D, and that is, I view this as a map where I take a symmetric form, yeah, of a certain degree k, T star Q, so that's a differential form, but only symmetric instead of anti-symmetric, and I make a form out of it of 1 degree higher, in such a way that it satisfies a Leibniz rule for the symmetric tensor product. Yeah, so via Leibniz rule for the symmetric tensor product, and so it's a derivation for the symmetric tensor product, and locally in a local frame, we'll use this formula later on. So if you have a frame of local sections here, let's say not Q, but it's a local frame, so that's some open subset U in Q open with dual frame, let's say E upper indices, a dual frame on T star U, then you can write this, and that's just to fix the prefactors. So it's a covariant derivative in direction of the vector fields of the frame, and then you multiply with a corresponding one form, and that's obviously a chart independent, a frame independent quantity, and it satisfies a Leibniz rule. Yeah, so that's it's an the symmetrized covariant derivative. So once you have that, the last ingredient to cook up a simple calculus is the multi insertion, symmetric insertion. So that's a pairing of symmetric multi-vector fields into symmetric forms. Yeah, so I insert sort of symmetric multi-vector fields into symmetric forms, and I get back a symmetric form of lower degree. And you see if I reach negative things, then it will be just 0. I have inserted too much, there are not enough slots. And how do I do that? Well, I first say that on a symmetric tensor product of vector fields, it's just the composition of the insertions of the individual vector fields, and the individual vector fields inserted in a one form is this one plus Leibniz for V. Yeah? So if this is just a one form, then it's the natural pairing, and I require a Leibniz rule for the symmetric product of forms. Yeah? So so that's just so it's not, depends a bit on your convention. It's not just a natural pairing, but there may be some factorials involved. Yeah, but this is the good algebraic behavior here, that it becomes a homomorphism of the symmetric tensor product concerning the multi-vector fields, and it's a derivation with respect to the symmetric tensor product for Leibniz rules for a single vector field. Yeah? I mean, that the higher ones are of course not derivations anymore. Yeah? They are sort of higher differential operators. Okay, now we can do we can reinterpret. Is there a question? No, I think this is correct. The x's are tangent vector fields, symmetric tangent vector fields, and the alpha will be the forms. And I insert multi-vector fields in multi-forms. I mean, all symmetric ones. Yeah.
Right. So, but in your last slide, didn't you say that like the tangent was the function, right? Isn't it like even more
here,
like over here, right?
Yeah, I take polynomials on the cotangent bundle,
which is the tangent,
and
right?
that are the symmetric tangent vector fields. Yeah.
Right. Exactly. So I thought a tangent serves as functions on like a polynomial functions. Therefore, if you want to have a duration on functions,
you will see how things match together. I mean, this is I mean, you agree that this works, right?
Yeah,
that works for any vector bundle and its dual bundle. Yeah, that is not specific to the tangent and cotangent. Yeah, it's just vector bundle and dual vector bundle. And here, okay, the covariant derivative has not made yet an appearance, but this pairing here you also have for any vector bundle and dual vector bundle and symmetric tensor powers of them. Yeah, and I will need it in this way. Yeah, because I define now the does it clarify the you will see how I use it. Yeah, then you will see it. So this allows us now to define what is a standard ordering. Yeah, I would like to cook up out of a polynomial function on my symplectic manifold T star Q, I would like to cook up a differential operator row standard of this function. This should become a, of course you can. I would like to cook up a differential operator acting on functions on Q. Yeah. So this is what standard ordering should do. And without restriction, a polynomial can be written as J of X. Yeah, that's this algebra homomorphism. That makes formulas more simple. Yeah. So how do I define this? Well, I should tell you how it acts on functions psi. Psi will be a function on the configuration space. And the formula I'm using is the following. So first of all, there's some h bar inside, of course. Then there will be the symmetrized covariant derivative in the exponential series acting on psi. So that is something, if h bar would be a formal parameter, that is something like the formal symmetrized Taylor expansion with respect to this covariant derivative. And into this guy, so this will be in the Cartesian product of, if you scroll upstairs here, of symmetric forms on Q. Yeah, all degrees appear. Yeah, D is applied over and over again. Yeah, and in this guy I insert X. So x has only finitely many degrees. I insert x in these multiforms over and over again. Sometimes I get 0, sometimes some pairing remains, and there will be forms remaining. And sometimes the degree of x matches the degree of this exponential, sometimes. Yeah? And I just get a function. Yeah? And this function is what I keep. Yeah? And that is this, which I call the restriction to functions. Yeah? So this is the, I should explain now these terms. So this is restriction to function part. Yeah? And now you see this formal exponential series is harmless. It has infinitely many terms, yeah? But inserting something which has only finitely many different degrees can only produce a finite number of terms where it matches the degrees to get a function. Yeah, so this is a finite summation. Yeah, this exponential series sort of can be stopped at the maximum degree of x. Sebastian. Ah, yeah, you need a microphone.
Yeah, I mean, typically, if you have something in a symmetric algebra and you pair it with something else in a symmetric algebra, then you might get factorials or not. And I think the most natural thing would be to have a quotient version on one side and a subspace version on the other, and then maybe everything matches up just.
I think this is sort of implemented by this property here.
And now I'm just curious, if you write an exponential series there, that gives you a bunch of factorials. Do they account for the fact that in one place you took a subspace instead of a quotient, or the other way, or whatever?
It's a good question. The point is, if you work out this formula in the flat case, yeah, you reproduce exactly the formula I gave you in the first lecture. This is the formula. Yeah. So if this is and you don't need much. You only need to know that this is an associative product. Mm-hmm. Yeah. That this is therefore a derivation. You only need this formula here, and that this is extended as a derivation if it's a single vector field. With these combinatorics, everything is fixed and matches and reproduces this flat situation I had in my first lecture.
Okay.
And that's the cool thing. This formula looks pretty nice, right? That's the nice thing. Yeah. So I should mention that remark. Yeah. So this is a finite sum. Yeah. And so this exponential series is not I mean, this for degree reasons it's easy to see, and it reproduces the row standard from the beginning.
Okay. So it's not like just taking the infinity jet of psi. That's not what the exponential does.
Yeah, well, infinity jet is something in the jet bundle. It's not in the and you need to identify the jet bundle in a clever way with powers of the symmetric forms.
Yeah, that's what the connection does, right?
And that's what the connection does. And but there you can, in principle, smuggle in k factorials for each degree. And this is done in a clever way so that this really matches well. Okay. So this is in some sense the infinite jet. Yeah, this is the formal Taylor expansion of psi using the connection. Yeah, but it's well, the point is you cannot go along without a connection, because in jets you can't insert multi-vector fields. That's the point. Yeah? I mean, you need to invest a connection at some point. You can talk about the infinite jet of psi directly. That's intrinsic. Yeah, but then you cannot insert the x in there. You don't know how to pair. Yeah, and that's where you need a connection. So either way, you need a connection. Yeah. So I use it directly and avoid the language of jets. Yeah. Then it's sort of parametrized linear algebra. Yeah. This is yeah. So it's clear that all these pairings make sense. Yeah. And it's a good exercise to figure out the things in the flat situation, that you have exactly the combinatorial factors as you want. Yeah. As you want them for this standard ordered thing. Yeah. Martin.
That this is Taylor expansion in normal.
Yeah, that's another way to see that. Yeah. The remark of Martin was that this is sort of the, if you would omit the IH bar here, yeah, then this would be the formal Taylor expansion in normal coordinates at a point. That's exactly the formal Taylor expansion of psi. So if you fix a point, go in a normal chart for this connection, then it is. And the point is, I smuggle in this IH bar. You could also smuggle it in front of the x's. Yeah. But that's sort of more funny to do it like that. Formula looks nicer. Yeah. Formula looks nicer. Okay. So this is the standard ordering, and then what you get is really a global simple calculus, in the sense that this produces all differential operators on Q. It's compatible with the filtration. I mean, the differential operators are no longer graded, but this is as its function linear, of course. Left linear differential operators are a left module there. It's really important, and so this is nice, and it has a price. The price is you need to use a connection. Yeah, so that's one thing. And then because this is a linear isomorphism, you do the same thing as we did in the beginning. You pull back the operator product. Yeah? So you define the standard ordered star product, depending on the choice of the connection, to be the composition product of differential operators coming from this standard ordered symbol calculus, global symbol calculus. Yeah? And this, for sure, it's associative, yeah, by definition. Yeah, and it's not so easy to see that it is a star product in our sense. Yeah, that it is bidifferential in F and G. Yeah, this took us quite some time to understand, actually, and it's not so easy. Yeah, because you can sort of mess up and use slightly different formulas instead of this one. You could mess up with this formula, and then you lose immediately differentiality. Yeah, so you would get, in a fixed order of H bar, infinitely derivatives in momentum direction, which on polynomials doesn't make any difficulty, but it's not a star product anymore. Yeah, so this is a star product on T star Q for the canonical Poisson bracket. And such that the polynomials, and I only constructed it for polynomials, and there everything was polynomial in H bar, is a C of H bar, only polynomials, subalgebra. Yeah, so our first step in the wishful thinking is fulfilled. We have found a subalgebra where everything converges for trivial reasons. Yeah, for it's a finite sum always. Yeah, so our step one, we have the big green hook. Yeah, so let's do that. Yeah, and so in some sense, what you now want to do, yeah. But I will show you just another star product to convince you that this is something interesting to be done. In some sense, you could start now to cook up locally convex topologies in this situation, and try to make this thing continuous, yeah, as our program says. Yeah, and for the cotangent bundle of a Lie group, we are now luckily in the position to actually do that. Yeah, but in general, I have no idea. Yeah, so this is it's clear that in this expression, when you compose these differential operators and reorder them again to make compute this inverse, you will pick up a lot of curvature information of your covariant derivative, and that sort of makes the formulas completely inexplicit. I have no formula for this thing, explicit ones. Yeah, and that makes the analysis involved, and it will certainly involve curvature information, and you have to balance Taylor information against curvature information somehow. Yeah? And I guess in a generic situation, you cannot do much. Yeah? But okay. But before that, let me just introduce also the Weil-ordered version of this. Yeah, total symmetrization. How do you that? And the point is, you would like to cook up an involution. Yeah. So what do you choose? Is a volume density or volume form, if you don't like densities, mu on Q. Yeah, so that we can integrate a smooth one. Yeah. Think of a volume form if you don't like densities. Yeah, and then you can. There's a question. Maybe it's not even important. You can get along without it with torsion. Yeah, but okay. This is for.
So it does make easy the
traditional
computation.
Reasons, I would say it's important. I think you can get along with torsion as well. Yeah, but okay, yeah, it doesn't add much generality. On the other hand, it doesn't help you much, I think. No? Anyway, let's consider a volume density, and now what we want to do is to compute the adjoint of a differential operator, and we know all differential operators are standard ordered things of jx's for certain x's. Yeah? So and we want to compute the adjoint of this with respect to to the inner product coming from mu. Yeah? So this is Q, sorry, not phi. So this is over Q, and phi and psi are now, of course, compactly supported in order to make sense out of the integral. Yeah. So this is what we want to compute. Yeah. And yeah. And funny enough, there's an completely explicit formula in full generality, and for some reason this is not very much known. Yeah, but this is the following construction. So well, what do you need? You can expect, because we have chosen a covariant derivative and you want to do integration by parts. Yeah, so you have chosen a volume density. These two, they don't know each other yet. Yeah, so you need some kind of compatibility. Well, you don't need compatibility, but you need to know how the covariant derivative acts on the density. Well, and because it's a density, it will be a multiple of it. Yeah. So this defines some alpha in one form alpha. Yeah. So if you are lucky, then your volume density is covariantly constant, then alpha will be 0, but doesn't need to be the case. Yeah, and in fact, in the case of the Lie group, this is not true in general. Yeah, this is only true if we have a unimodular Lie group later on. Yeah, so we have to take this generality here. Yeah? If you have a Levi-Civita connection, you can take, of course, the Riemannian volume density, then this is covariantly constant. Yeah, then integration by parts becomes a little bit more simple. But in any case, this is not really the problem. Yeah? So I have to hurry up a little bit. Sorry. So now what can we do? Yeah. So this is one thing, and you can do with a one form. You can lift vertically, because we are on a cotangent bundle, into a vector field, a vertical vector field on the cotangent bundle. So this is the completely canonical vertical lift. Becomes a vector field, a vertical vector field on the cotangent bundle now. Yeah? That's one ingredient we will need. Yeah, and the other is a little bit more involved. I will need a metric. Yeah, a metric G0. So that will be a metric on T star Q. will be a pseudo-Riemannian metric of split signature. And how do we construct that? And that's a cute construction. So what do? You choose a point in here in the cotangent bundle. And then what can you do with a tangent space at this point? Yeah. So inside the tangent space, we have the vertical space. Yeah. And that is, well, by definition, that's the kernel of the tangent map of the projection. And that is isomorphic to, as vector space, canonically isomorphic to the cotangent space. Sorry, that's not an alpha Q anymore. That's an Q. Yeah. So this is the vertical space. That's true for any vector bundle, right? That's the vertical space. Yeah. And that's always isomorphic to the fiber, right? And now we have a connection. So we get a horizontal lift. And therefore we get a horizontal subspace. At alpha Q inside the tangent space at alpha Q. And funny enough, the horizontal space for any connection in any vector bundle is always isomorphic to the tangent space downstairs. Yeah? So the horizontal space, that's the tangent space downstairs, always. Yeah? And now the funny thing happens, and that only happens for a cotangent bundle, is that the vertical space and the horizontal space are naturally in duality to each other. So we can naturally pair. Yeah? So G0 is natural pairing between horizontal and vertical spaces. Yeah? Yeah? At every point. That's this G0. So it depends on the choice of a connection, and I don't know, that probably has many names involved. I think in this, we found this in this book of Jano, I guess. Yeah, this is probably, well, I don't know. There might be many names, and it has split signature because it's a pairing of vector space and dual space. Yeah? Okay, so anyway, it's a Riemannian it's a pseudo-Riemannian metric. So it has a Laplacian. So, or D'Alembertian, yeah. So it has a Laplacian, and yes. And now the funny thing is, what you do is the following: you look at the following operator n on functions on the cotangent bundle. You use this Laplacian. You take a formal exponential series with this Laplacian, and with a Lie derivative in the direction of the vertical lift of this alpha coming from how non-covariantly constant the density is. Yeah. You plug these two together, make this formal exponential series. There will be an h bar. And the vertical lift that lowers the momentum degree by 1. It differentiates in vertical directions, right? And this Laplacian, I should also tell you that the prefactors, I mean, in natural pairings, you can smuggle in some factors of 2 if you want. So the normalization is such that the leading symbol of it is such a thing, yeah? So, and then there will be lower order terms. So it steals 1 momentum. That's the important observation. Yeah. So it also lowers the momentum degree by 1. So both of them do. And therefore, if I apply this n to polynomials on T star Q, that is a well-defined endomorphism. And it's in fact a bijection. Yeah, I mean, the exponential series terminates after finitely many contributions, as long as I'm acting on polynomial functions in the momentum. Both of these operators steal one. Yeah, and exponentiating doesn't. This exponent is nilpotent. Okay, and now little theorem is you can compute the standard ordered adjoint of this guy. So that will be the following. It's again a differential operator. Therefore, it's a row standard of something, and the something is just n square of this function here, acting on phi psi. Yeah? So that's the. I better should, yes. And it's in here. Yeah, sorry. Yeah, so of course, yeah. Yeah, so N stands for Nikolai Neumeier. Yeah, that's what he did in his diploma thesis. I mean, it is if you want, this is just integration by parts. Yeah, but it's a kind of involved integration by parts because you need a lot of covariant derivatives, and they produce additional Christoffel symbols all the way. And so what you can do is so you can define the Weil ordering of a function as the standard ordering of NF, and then you see that this guy is sort of behaving nicely with respect to adjoints and complex conjugation, and you can also define the Weil ordered star product. Yeah. So that reflecting this sort of better symbol calculus, the Weil ordered symbol calculus, by just using this n as an algebra isomorphism. Yeah? And as long as we're working with polynomial functions, this is all well defined and nice. Yeah. Okay. So far, I think that's all what I need on general grounds for general cotangent bundles. Yeah. And as I said, polynomial functions in the fibers, they form a nice subalgebra isomorphic to the algebra of differential operators. And the big task would be to find locally convex topology for them such that the product is continuous. Equivalently, you can ask yourself the question, is there a locally convex topology on the space of differential operators such that the operator product becomes continuous? I have no idea. And I would suspect no, as long as you consider arbitrary smooth coefficient functions. Yeah, for the sort of same reason that with the Borel lemma argument, this is probably not feasible. Anyway, now we go for very briefly for a Lie group, and let's say connected Lie group. Yeah? And so what do we want? Yeah, we need to talk about the cotangent bundle of the Lie group, and you all know that this can be left trivialized into so the all cotangent bundle are trivializable, and I assume them to be trivial. So this is the one here. And the Poisson structure on the symplectic Poisson structure and the symplectic star products we have here, they have now a very, very nice form. So as long as we consider functions on here which are invariant under the point transformation, they will be just depending on the fiber. Yeah. So that's the invariant functions. And here we have there are a lot of G's. This is now Simon Gutt. Yeah, that's the Gutt star product from before. Yeah. What we have. And in fact, Simon Gutt did something completely different. She was not only interested in G star, but in the cotangent bundle. So in her paper from '83, she used this observation, and the construction of this Baker, Campbell, Hausdorff, Poincaré, Birkhoff, Witt star product on G star to induce a star product on the cotangent bundle of the Lie group. And in fact, it turns out that this is the Weil star product I'm talking about here. That's the one she constructed slightly differently. But the point is that the Weil, and similarly the standard ordering that only involves sort of the G direction. So as long as you're talking about G invariant functions, it doesn't matter. So they restrict to star Gutt on invariant functions. So that's good news. So we have already something where we understand convergence. Very good. So in the fiber directions, we can recycle all our crazy estimates from yesterday. And so we have now to worry about the star product of functions depending only on the group directions among themselves, and on the functions depending on the group direction with G star and G star with group. So these are the remaining cases. And now standard ordering is nice because if we have a function depending only on the group, and I define another function like that, then this is just a pointwise product. So their estimates are fairly easy. That's good news. And now I have to take a look with the standard ordering. I always forget. So this is also true if I plug in here something arbitrary. This is still true. So this will be still the pointwise product of the two. So that's a question. Okay.
So it is right to say that the canonical symplectic form in the cotangent bundle is it forms, so the symplectic form of so the cotangent bundle of a Lie group forms a double symplectic groupoid over two different Poisson structures, the zero Poisson structure on G and the linear Poisson structure on G star.
Maybe yes. No, I mean that you can view this in many ways. So this is really very down to earth what I'm doing.
And then you are saying that all the three quantizations of the three Poisson structures are compatible.
I mean there's one interesting piece. So so standard ordering in this way is not quantized, but the other way is. So here, if I have some J of X standard ordered with a function like that, that is non-trivial. That is the only non-trivial missing contribution. And here we know that J of X's standard J of Y, that is sort of the Gutt star product from before. That is we had defined that on the so if X, Y, which are then just elements in the symmetric algebra. That's sorry, not S, like this here. So the invariant polynomial functions, they are just elements in the symmetric algebra over the Lie algebra. So as yesterday. So so what do we have? We need estimates for this here. That will be pretty easy. For this slightly more general thing will be fine as well. For this last part we did yesterday, so that's all pretty fine. And so the only remaining piece which we have to take care of is this one. Once we have done that, then by associativity of the star product, we can sort of assemble arbitrary function times arbitrary function and get this done. Yeah. So what we need is to estimate for an invariant x, so it's simply an element in this vector space, finite dimensional vector space, standard ordered star product with a function on the base. Yeah. And so the point is, there we need a good function class, and I think because time is already a little bit further, I will just try to give you the conditions on the functions such that we get estimates here, continuity estimates. Yeah. So we need to specify nice class of functions on G. It's not Q anymore, it's G. On G. Such that third part can be estimated. And of course, I'm sorry, I forgot the most important thing, of course. I mean, I didn't tell you what initial data we use. Yeah, I mean, there's a connection to be used. Yeah, and the volume form. So the volume form, we take any left invariant volume form. There's only one up to scaling. And here we take the half commutator connection. So on left invariant vector fields, the covariant derivative is half of their Lie bracket. Mm-hmm. That's the most invariant torsion-free connection you can have on the Lie group. It is typically not a Levi-Civita connection. Yeah? So it is typically not unimodular. So there's typically no invariant covariantly constant volume density. This is true if the Lie group is unimodular. Yeah, that's exactly this alpha I defined is exactly the unimodular class. That's a trace of Gutt. Yeah? And but this is the good connection you use in the business. Yeah, this has the best invariance properties, the most canonical connection. If you have a B invariant metric, yes. So in a semi-simple case, you could it would be at least you have a pseudo-Riemannian metric such that it is Levi-Civita, and in the compact case, you would have an honest Riemannian metric such that this is Levi-Civita. Yeah, but okay, there are Lie groups which are non-compact. Yeah, no, but that's true. Yeah, then of course you also have then also the volume, the left invariant volume form is the volume form of the metric, and therefore it is B invariant, and everything is nicer. The alpha is 0 in that case. Yeah, but in general, the alpha is trace of Gutt. Yeah, it's the modular 1 form, and so it might or might not be 0, and the connection might or might not be a Levi-Civita, but okay, it's torsion free. That's all we need. Yeah, and it's nice. Yeah, so it has all nice invariance properties. So okay, sorry, I have to define now for a function the following quantity seminorms, and I use directly real analytic functions so that they are determined by their Taylor information at one point. Yeah. So a Lie group has a canonical analytic structure. Yeah. So I'm using that, and now I define the following. I fix again, you know the game. Yeah. Some parameter R, and typically R will be bigger than 0. Can probably do things also for negative R, but that will not produce much interesting things. And then I use a parameter C, and then I define a seminorm of this function phi as follows. I take the Taylor information of the function at the group unit. So how do I do that? I take Lie derivatives I will explain this notation immediately, in direction of a basis of left invariant vector fields, and this is a multi-index. Yeah? And I have to sum over all these multi-indices. So that's a guy of length n, and we have no, this is bad notation. Yeah, this is going from. This is a multi-index. I hope I get this now right. Yeah. So this goes from 1 to the dimension and k numbers like that. We'll take absolute value of all these Taylor coefficients. So the x's are, so the x1, xn, this is a frame of left invariant vector fields, and Lx alpha is simply Lx alpha 1 up to Lx alpha k. Yeah, so that's the Taylor information, and with Lie derivatives, yeah, in left invariant vector field direction at the group unit. Yeah, and now you would say, well, Taylor expansion would require, if you a k factorial, because I talk about the derivatives and not the coefficients. Yeah, that's why I need a k factorial here. But then the r comes into the game, and that is sort of k factorial to the power r here. Yeah. So for r equals 0, this would really look like Taylor expansion as we had it yesterday. So that's in order to make it match with the conventions we had before. And now we had this scaling, this exponential number appearing. That's the c, and I will just plug it in here, let's say. So there's still a c to the power k. That is because last time we took all continuous seminorms. Now I take, in some sense, the norm corresponding to the L1 norm of this basis. Yeah, but that is not all norms. I need to take multiples of it, and this c takes care of the multiples. Yeah, and now we define ER of G to be those real analytic functions such that this QR of C of phi is finite for all C positive. Yeah? It doesn't depend on the choice of the frame, and this will be a nice subalgebra of real analytic functions. And in particular, if E0 sort of deserves the name of being entire functions on the Lie group. Yeah? Yeah? So that's the condition, and it's sort of important that we take the absolute values of the Taylor coefficients individually and not only of the sum. Yeah, so that really makes a difference. Yeah, and the statement is first statement is, if we take such coefficient functions with a symmetric algebra over G star as yesterday, with the tensor product, pi tensor product of the two, and we take R at least 0 and R prime at least 1. So the best cases are 0 and 1. Then we get the largest spaces. Can take the completion of all of that. Then star standard, and the same for star while, are continuous. Let's maybe erase the completion. First, you show continuity, and then it extends to the completion. Yeah. So that's the theorem. Yeah. So our step 2 is achieved. Yeah. Hope was granted. Yeah. We found continuity. Now, of course, this has a little price. Yeah. Up to now, I defined you a funny space of functions. Yeah. But I didn't tell you which functions are actually in there. Constant functions for sure. But are there more? Not so easy. Yeah, I mean, we require directly to have a function defined on the group, specifying only its Taylor coefficients at the group unit, and requiring some ability of them. So it might well happen that locally around the group unit, this function, that there is a function, but this the group might sort of forbid to have a globally defined function getting out of this locally defined thing. Yeah, so it's not completely obvious that this space is non-trivial at all. Yeah, and that is actually the second part of the statement. To be sure that if phi in C omega of G is a representative function, i.e. has finite dimensional, I think that's the definition, right? Finite dimensional G orbit. So if I apply left translations to the function, take all the functions I get, they sit inside a finite dimensional subspace of functions, then phi belongs to at least E0. Yeah. So for most Lie groups, many Lie groups, you have zillions of representative functions. Any finite dimensional representation of your Lie group gives you such functions. And if it's a matrix Lie group, then they are point separatingly many. If not, then you might lose a couple of them. Yeah. But still, this shows you that there are zillions of these functions inside this space of entire functions. Yeah. So that's good news. Yeah. There are a lot of functions. They are more than the representative functions because we have sort of this space itself is infinite dimensional, and it has sort of you can take sums of them in different representations and do some completion things. So this is slightly bigger. On the other hand, it's clear that it is a condition on the Taylor coefficients. Yeah. So it's not just any function is in there. Yeah. So it's really a condition. And yeah, so I think this is maybe a good point. Maybe a last theorem is that if we have f and g in this ER of G S of G star, and take also the completion is now possible, the product extends, then the star product is really either standard or while. That is an entire function of H bar. And the Taylor expansion of it is the formal star product. And that converges really in the above topology. So that's the pi topology we use here. Anyway, these spaces are nuclear. Again, also ER is nuclear, so there's not much of a choice for what topology on the tensor product we use. Yeah. Okay, so I think I should stop here. Jonas is getting nervous already. And I should stop here. And as promised, I will give you the precise references in this document later on. So to get the credits correct here for all the things I told you. Okay, thank you.
Thanks, Stefan. Thanks, Stefan. So are there questions?
Here's a question. Yeah.
First, thank you very much for the wonderful talk. I like a lot your step 1, 2. It's really inspiring and very clear. I'm wondering You know, what you do over here, like T star Q, it's something like a first example of symplectic symplectic manifold, right?
Yeah.
And somehow you can apply your there's some intuition there. You can apply your machinery and formulas, correct formulas, and I wonder, just go like one step further. Or in your lecture note, the next symplectic one, which is TQ Q, like what means that?
Okay.
Just it's like it's an example. It's like the first two symplectic thing.
Okay. So higher symplectic in the sense of higher symplectic.
Right.
Yeah.
Exactly. Easy. It's like a. And one. I guess no one really knows how to quantize them, but maybe with I already see like you have this pairing, you see this T star Q, TQ, you have this G0, this pairing.
Okay.
It's a very
so the question, maybe I repeat, I don't know if everybody heard, the question was whether there are some higher versions, higher symplectic versions of cotangent bundles which are of interest and heading towards Courant algebroid things. And well, I don't know if there is a generally accepted notion of what is a quantization of a Courant algebroid. Yeah, I have one paper with a former PhD student, Frank Keller, on where we cooked up one possible definition and showed existence using a Fedosov quantization on this corresponding super manifold business, and we use not super language because I'm not able to do that, but more conventional vector bundles, connections, and all these. Yeah, so there one can use a Fedosov construction, which originally Martin did in the 90s. Yeah, this super version of Fedosov, and that cooks up a star product, and then one can ask whether this degree 3 element quantizes into something nilpotent or not. Yeah, and that becomes a condition. Yeah, that's not for free anymore. Yeah, so in order to have something, yeah, the star product is associative, but the structure encoding the Courant algebroid is this element 3, this which has super Poisson bracket 0 with it, and now you want it into super commutator 0. Yeah, and to quantize that, this really becomes a condition. There are positive and negative answers to that question, yeah, depending on the situation. Of course, you can try to play the game with convergence as well. Yeah, but that is yet a step further, I would say. Yeah, so this is I mean, it is morally still a cotangent bundle, so that's the good news. Yeah. Bad news is that it's not a group anymore. So I can't do it immediately, right? And going beyond groups here would be my first step, to go to other configuration spaces and try to extend this construction. And you see, I mean, here in the definition of this functional space ER, yeah, you use a lot that you have a group.
I see. So
yeah?
you would
this is really, you need this global frame in order to use this Taylor information business, and so it is really very, very much Lie group technology.
Right,
yeah,
right,
and maybe one can go to some homogeneous spaces or something. That would be my next step somehow.
Yeah, that would be great. So maybe one just make a little bit step further. Instead of Courant, we can also do some, G just extended by R. There will be a string group, and what would that be? Well, anyway, I talked to you maybe.
Yeah, yeah. I mean, this is all interesting. Yeah, of course. Yeah, that's one definitely can do that. Yeah.
Okay.
Should try.
There is a question from Simon.
From Simon. Hello, Simon.
Hi, Stefan. I enjoyed your lecture. Thank you. I was wondering, do you know if the group is compact, what you get? You already have all the representative functions, and of course you have Peter-Weil's theorem, which says that there are sets in L2. So do you know more?
In the compact case, I guess what one can do more, which we haven't, but what one can do more is, of course, to take these functions in ER, which are integrable now, right? So you can integrate them. In particular, you can integrate them over the configuration space, which is the group. And therefore, this inner product makes sense in the compact case. And therefore, sort of restricting a big function of the cotangent bundle to the configuration space, which is the compact group, and integrating them is a functional on the algebra. And for the Weil product, with some little tricks, this is a positive functional, giving as GNS representation precisely this one here. Yeah. So I guess in the compact case, one can sort of mimic the formal construction of representations for cotangent bundles and GNS and all that for this convergent situation. In the cotangent bundle case, we were sort of using this function only for compactly supported functions. As long as you stay in the smooth setting, this is no big deal, yeah. But of course, inside here, there are not too many compactly supported functions unless the group is compact. Yeah. So that's, but then I think you can really start doing representation theory and maybe reproduce some kind of, well, probably well-known stuff, yeah. But would be nice to get hold of that from that point of view. Yeah? Okay. So compact groups are definitely worth a second look here, yeah, of course. Yeah.
Thank you.
Okay, are there more questions? This doesn't seem the case. Then I suggest we thank Stefan not only for today, but for the whole week and the very cool mini course.